Okay, this is 10-4 in Advanced Geometry, and today we're dealing with how does volume or surface area change if we affect some of the dimensions, like by doubling the radius or doubling the height or doing stuff like that. And it's going to start out, it's actually a pretty easy concept. It takes a little while to get used to, right? So it starts out a little weird. So we'll just do 4 problems pretty much the same in a row here. Number 1, how does the volume of a box change if the height is doubled? So here's how we're going to do this. This is the easiest possible way. They're talking about volume of the box. Let's start with the formula for volume of a box, which is the length times the width times the height. Okay, so whatever kind of shape they're affecting, let's start with that formula. It says if they double the height, all we have to do, since they're talking about height, is let's go find that variable in this equation. Right, that's h, right? And let's do this. They're going to do this. They're going to double the height. So I want you to write the formula down, put this little arrow right here, and put a little 2 here saying that they're doubling it. That's what double means, times 2. Then whatever number this is right here, we got to take that number and raise it to the same power that that variable is being raised to in this equation. And h is being raised to the first power, so is w to the first power, l to the first power. Like there wasn't an exponent there, so that's really a 1. All we have to do is take 2 and raise it to that power. And what number is going to shoot out of there is 2 to the first power is 2, so that's what's going to happen. That means that the volume is going to be multiplied by 2. If I had a box and all I did was double the height, that changes the volume by a factor of multiplying it by 2. Let's do that down here on number 2 again. Let's start with the formula, and I've kind of cheated and put all the formulas right away because all 4 of these are about volume of a box. Right, so magic, that just showed up. Wow. But so I got all my formulas written down because all 4 of these problems are talking about volume of a box. So if you want to do that, go ahead and write all the formulas down also. Number 2 says, how does the volume of a box change if the width and the height are doubled? So they affected a couple dimensions. First they affected the width, so I'm going to do this. I'm going to put a 2 down there because they doubled it, right? So that means they're going to take the width times 2. And they also did that to the height. Now what I have to do is take this number and raise it to the same power that that variable is being raised to. 2 is being raised to the first power, so what's going to shoot out of there is a 2. And then same thing here, this 2 is being raised to the first power, so what's going to shoot out of there is a 2. And now what's left is these 2 numbers. They have to get multiplied together because that's what operation was going on between a w and an h. They were being multiplied. So really, the volume is now going to be multiplied by 4. Because I doubled the width and I doubled the height, right? That's going to affect the overall volume by multiplying it by 4. On number 3, how does the volume of a box change if all dimensions are doubled? So that means they're going to double this bad boy, they're going to double that bad boy, and they're going to double that bad boy. And all of these are being raised to the first power. So what's going to shoot out of here is 2 to the first is 2. What's going to shoot out of here is 2 to the first is 2. And what's going to shoot out of here is 2 to the first is 2. And we just need to multiply all those numbers together. 2 times 2 times 2 is 8. So the overall volume will be multiplied by 8. If you double the width, double the height, and double the length, the overall volume would be multiplied by 8. So that's just a quick example of 3 things. Now let's check out number 4 here. How does the volume of a box, so same formula, right? Volume of a box, change if the height is tripled, so we got to throw a 3 there, and the length is doubled. So the length, we're going to throw a 2 there. And we just got to go one thing at a time. We got to take this 2 right here and raise it to whatever power that variable is being raised to. So 2 to the first will shoot out a 2. And take this 3 and raise it to that power. So what's going to shoot out of there is a 3. And we got to multiply those together because that's what's going on up there. So that would affect the overall volume multiplied by 6 right there. So if you double the length and triple the height of a box, this volume would get multiplied by 6. So that's the basics. That's the easiest formula that we have for volume is length times width times height. What happens if we change it from a box? Now we got volume of a cylinder, which we haven't actually even done yet. If you go to your yellow card and check out the formula for volume of a cylinder, it's on there. It looks like this: volume equals capital B, which remember that stands for base area. So let me make it nice and clean here. Base area times height. Right, that's the formula for volume of a cylinder, which that's the generic formula. If you see it says for a prism or a cylinder, right, on the yellow card. What we really have to do is we have to kind of tweak this formula and change this capital B to whatever shape the base is for this particular guy. Since it's a cylinder, isn't the shape of the base a circle? So like the formula for base area for a circle, it would all get changed to pi r squared, because since the circle is a base, since the base is a circle, its area is pi r squared, so the red thing stands for the base area and h stands for the height. So here's the formula for volume of a cylinder. That's the real formula. This purple one up here is the generic formula. It says, how does the volume of a cylinder change? So we start with the formula. If the radius is tripled. So what I have to do is whatever variable they just affected, they affected the radius. I'm going to go to that in the formula and throw this guy down there. I just tripled the radius. Now I got to take this number and raise it to whatever power that variable was being raised to. Ooh, it was being squared, so what's going to shoot out of there is 3 squared, which is actually a 9. If you had a cylinder and you tripled the radius, the overall volume would get multiplied by 9. That's the answer to this question. Then if I keep rocking on number 6, 7, and 8, they're all talking about volume of a cylinder, volume of a cylinder, volume of a cylinder. So I got that formula written down each time, pi r squared times h. Go ahead and do that if you would. And then number 6 here says, how would the volume of a cylinder change if the height, is quadrupled? So they affected the height, so I got to go to that variable right there, and quadrupled means times 4. So we're going to take whatever number this is and raise it to the same power that that variable is being raised to. Well, h is only being raised to the first power, so I just got to take 4 to the first power, and I get multiplied by 4 to the first power is 4. So if I had a cylinder, and if I quadrupled the height, that's only going to change the volume by multiplying it by 4. So it's just check out the variable that they affected, go to it, and raise that number to whatever power, whatever exponent that variable is being raised to. Let's check out number 7. It says, how does the volume of a cylinder change if both the height and the radius are doubled? So the height's been doubled, ba-boom. The radius has been doubled, ba-boom. And we just got to go one at a time here. I got to take this 2, raise it to the power that r is being raised to, and what's going to shoot out of there is a 4. I got to take this 2, raise it to whatever powers that h is being raised to. 2 to the first power is 2, and then cha-ching, the operation going on between them is multiplication. So multiplied by 8 is what really ended up happening. If the height and the radius were doubled, the volume of a cylinder would change by being multiplied by 8. Let's try number 8 now. How does the volume of a cylinder change if the height is multiplied by 5? So like that, and the radius is quadrupled, multiplied by 4. So now I got to do this. I got to boom, take 4 and raise it to that power, and what's going to shoot out of there is a 16. Then I got to take this 5 right now and raise it to that power, and what's going to shoot out of there is a 5. So then you punch that in, and 16 times 5, should have done that in my head, is 80. Multiplied by 80 is what we get for an answer on that one. Keep on rocking. Now, whoa, now we do another curveball. How does the surface area, magic word area, change if all the dimensions are doubled? I want to check this out. Look at these next 4 problems. Magic word, all dimensions, all dimensions, all dimensions, all dimensions. This shortcut back here on the first 8 problems, works really cool when they affect like one dimension by this and another dimension by that. Like here they quadrupled this and took this times 5, or they tripled this and they doubled that. That's a cool trick over here. But if they do all the dimensions by the same amount, like here they say all the dimensions are doubled, all the dimensions are tripled, all the dimensions are multiplied by 2/3. All the dimensions are multiplied by 3/4. Here's a really, really cool shortcut. Whatever they're talking about, in number 9 they're talking about area. All you have to do is take whatever number they gave you, whatever they're affecting it by, they're doubling it, and raise it to the power that the label for that thing gets. Doesn't area's label, isn't it units squared? Right? So we just got to take that number and square it. And if you take 2 and square it, that would mean that this thing would get multiplied by 4. This trick only works if you affect all the dimensions, all the dimensions, all the dimensions, all the dimensions by the same amount. So it's just raise it to the same power that the label gets. On number 10, they're talking about surface area again. Area is what they are doing, and they did all the dimensions. So the label on area is units squared, and they're tripling stuff, so you just got to take 3 and raise it to that power, and you get multiplied by 9, baby. On number 11, how does the volume of a cylinder change if all the dimensions are multiplied by 2/3? So volume, isn't it units cubed? And since all the dimensions are being affected, I can just take whatever number this is and raise it to the same power that that thing would be. And if you take 2/3 and you want to cube it, that's really easy. You just take 2 and cube it and get 8. You take 3 and cube it and get 27. So that means the volume would get multiplied by 8/27. How does the volume of a box change? So they did volume again, which is cubic units, if all the dimensions are multiplied by 3/4. So since they did all by the same amount, and we're talking about volume, we'll raise it to the 3rd power and get a 27 right now, and 4 to the 3rd is 64. So multiplied by 27/64. I cannot write. What would happen to the volume of a sphere if the radius was tripled? So volume of a sphere is 4/3 pi r cubed. They tripled the radius, so take that to the 3rd power, and what shoots out of there is a 27. So multiplied by 27 is what would happen. What would happen to the surface area of a sphere? So surface area of a sphere is 4 pi r squared if the radius was multiplied by 5. So 5's got to get squared, and what shoots out of there is a 25. So multiplied by 25. The diameter of planet Summer is 7 times the diameter of planet Alex. How do their volumes compare? Well, you don't have to draw these pictures. I just wanted to show you because, see, they're talking about volume of planets, and a volume formula is 4/3 pi r cubed, since we assume that planets are mostly like spheres. But see, there's no diameter in this formula. What I want to show you is if the diameter is 7 times as big, so let's say that this bad boy had a diameter of 2 right here, and the diameter of this bad boy would be 7 times larger, which is 14. But how do the radiuses compare? If the diameter of this dude is 2, shouldn't the radius be 1? And if the diameter of that dude, red's not going to work, if this dude is 14, shouldn't the radius be 7? Well, look, the radiuses are still 7 times as large. So when they affected the diameter by 7 times, the radius also got affected by 7 times. So that means they multiplied the radius times 7. We need to raise that to the 3rd power, punch that in, and get 343. So it would be multiplied by 343. So there we go. Jimmy makes Nerf balls. He has to put a special fabric around each ball after they are made. The diameter of the orange Nerf balls are 3 times the diameter of the green Nerf balls. How many times more of the special fabric does the orange Nerf balls need compared to the green Nerf balls? So they're talking about a ball, which is a sphere, and they want to put fabric around it. That is like the surface area. So that's 4 pi r squared. And if the diameter is 3 times as big, so is the radius, as we've seen from previous problem. So that means a drop of 3 here, it's got to get squared, and what shoots out is a 9. So you'll need 9 times more special fabric. 9 times more special fabric. And the excellent Mathland problem. Mathland is a small town. The water tower is a right cylinder, mind you, that is 300 feet tall and has a radius of 15 feet. Old Susie's going to paint the tower hot pink to make the neighboring town of Englishland very jealous. If each gallon of paint can cover 325 square feet, how many gallons of paint should she buy, etc.? Let's start with a picture. Right cylinder. Use your geometer to draw a beautiful right cylinder like so. Then let's put the inflammation into that picture. The thing is 300 feet tall, so that's like the height of that bad boy, 300 feet. And it's got a radius of 15 feet. We're going to paint the thing. So that means, what do we want? Lateral area, surface area, volume. Painting, we kind of, sort of, maybe want the surface area. Kind of, sort of, maybe. But before we can find surface area, we definitely need to find the lateral area, which according to the yellow card is 2 pi r times the height. So if the radius is 15, I'll take that times 2 and get 30 pi right away. And the height is 300. And doing a quick multiply, we'll get 9 with 3 zeros and a pi. We're going to leave it just like that. Then the surface area of this bad boy is the lateral area, and now just a plain old cylinder would be plus both bases. The question is, should we paint both bases? We definitely believe we should paint the top one, because even though you're like, well, you never see it, how do you know? Maybe you're in an airplane. But the paint is not just for you to see necessarily, it is also to protect against like rust and etc. So we definitely want to paint that. But do we want to paint the bottom one when the ground is right here? I don't think that we need to paint that because it's grounded to the ground. Yes, grounded to the ground. So we only need one base area, not both base areas. Even though the formula for surface area of a cylinder is 2 times both base areas, we just want one base area. One base. So the lateral area was 9,000 pi. And one base area is 225 pi. Hey, put a 5 there. Then add those together and get 9,225 pi square feet. Now, awesome way of proportions. 1 gallon of paint can cover 325 square feet. Why do I erase my tower? I want to know gallons over square feet again. I know how many square feet I need to paint. I need to paint this 9,225 pi square feet, and I don't know how many gallons of paint, so cross multiply and get 325x equals 9,225 pi. To solve for x, you would divide both sides by that, and to the calculator I go. 9, clear it out. 9,225 pi equals this much divided by 325. Need about 89.2 gallons of paint. Approximately 89.2. But you can't go to the hardware store and buy 89.2 gallons of paint, so she's going to buy 90 gallons of paint. Then, how many gallons of water will the tower hold if there are 7.5 gallons per cubic foot? Gallons of water, that's a volume problem. This is a cylinder, so according to the yellow card, it's the base area times the height. Base area, 225 pi. Height, 300. Punched in 67,500 pi is the volume. Awesome, and that's in cubic feet.
But we don't really care about that. We want to know how many gallons of water it will hold. So here's what they tell me. 7.5 gallons is to 1 cubic foot. I will set up a proportion with gallons over cubic feet again. And what I know is how many cubic feet I have. I have this many cubic feet. And what I don't know is how many gallons of water that is. So this says X will equal, let's make it approximate, those two times each other. Do the calculator. 7, 5, 0, 0, pi times, that's a plus, buddy, times 7.5. Holy a macaroni. About 1,590,431.3 gallons of water. Now there is our answer. So that, my friends, was 10.7. Have a good one.